Let's begin. Good morning, everyone. I have a couple of announcements. So for ChatGPT usage, I'm not against it, as long as it amplifies you and augments your work. I would want you to limit it to improving your plotting capabilities, these things that are just kind of non-essential for an engineering education. Possibly it can help you understand the math, but you have to do the math. Now, in particular, for the coding pieces, like for project one, I'm looking at some codes and some people coming to and talking to me in the office. I can tell this is not your code, okay? And I'm not going to give you a hard time about it, but just sit and reflect with yourself about this, that what's the joy in that, right? Isn't it more powerful and empowering for you to figure it out? Maybe ChatGPT gives you some code. If you can't figure it out, rewrite it on your own, please. Okay, because I can tell that. I can tell what's going on. And specifically with what's coming in the next few weeks for the lectures, there will most likely be an exam on this material. And so if you use ChatGPT for your homework, and I give you the same problem in your exam or a similar problem, you will be in trouble if you didn't do it yourself. Even if you copied from GPT, that is not sufficient. You have to put enough effort to understand what GPT is doing, if it's helping you out. So you're mature, grown-ups. I leave it up to you to make that determination, but that's my advice to you. And it's interesting because it's unfair to you because you live in this generation where it's like when they invented the CD and we were using cassette tapes, and then I went through that. I was like a die-hard cassette tape. We put it in these. You probably don't know what I'm talking about. We put it in these pencils and to spin it or rewind it, right? And then, but it's unfair to you because you haven't really gotten into learning how to code or get into the experience with math and theory, right? To me, GPT is super empowering, but I can call BS all the time when it's trying to make me happy. It just makes up stuff, literally makes up stuff. But you can't say that, you can't tell that yet, right? So you have to be careful, all right? And that's unfair to you because you live in this world where there's this amazing tool, you haven't had the chance to learn things in depth. So just be careful, be responsible about it. Announcement number 2 is good news. So I was thinking today that we did 2 projects instead of 2 exams. And normally an exam would take up a full lecture, so it would take time. So I think at the pace we're going, I think I'll let you off the semester like a couple or 3 lectures sooner if I finish everything on time. Okay, that makes sense? Because we didn't do exams, instead we just kept doing lectures and lectures. So I'll reserve, if I cover all the material I want to cover, which means I should stop talking probably and just get to the material. Yes, okay. So last time we left off at vector fields. Hold on. Vector fields, correct? Yes, we talked about the gradient. So we talked about vector fields, and these are fields of vectors, just like when we talked about scalar fields. These are fields of vectors that vary in time and space. And normally I would write this as U boldface, and this boldface X, which represents position, could be XYZ in Cartesian, easiest, or could be cylindrical polar, or spherical, or ellipsoidal, any other coordinates. This is a position vector, really. Generally is written as X or R, boldface and T. This means that, so this is a vector. It has in 3D space 3 components. Each component is a scalar field. Okay, think of it this way. So you're combining 3 scalar fields that are related. They make up a vector field. The first, once you talk about vector fields, you have to talk about calculus, because you're looking at, calculus means studying the change in something. So you're talking derivatives and integrals. And the fundamental operator, when we're thinking about change in vector fields, it needs to be a vectorized change. So a combination of derivatives in the x, y, and z directions, or in the r, theta, and z direction, and so on. So we define the nabla operator here. I'm defining it in Cartesian coordinates again for simplicity. And think of this as those three derivatives in each direction together combined to form a vector. And I want you moving forward to think about this nabla operator, or the del operator as we called it, to think of this as a vector itself. I know it's not a vector because you don't know where it has to apply to something to produce a direction. But in and of itself, think of it as a vector, because that will be helpful in developing intuition once we get to divergence and curl. Nabla is a linear operator. So if you're applying nabla on a scalar field times a constant, then that's equal the constant times the gradient of scalar field, and sum of two scalar fields. It commutes with them or distributes with them. So grad f1 plus grad f2. And then we asked last time, we defined the gradient of a scalar field. We did that last time, and that resulted in three derivatives, one in each direction. D phi, you're looking at the change in x and y and in z combined together as a vector. And we said that the result of grad phi is a vector. Now, what does the gradient mean? We left off last time talking about the example. In 1D, the first derivative, if you take a 1D problem, and if you look at what the first derivative is telling you about the curve, if you're going up, the first derivative, if you're going up a hill, the first derivative is positive. If you're coming down, it's negative. Now, if you assign a vector at that point in 1D, it's either going to point in the plus I or minus I direction. So if you're going up the hill, df by dx is positive, which is just the first component of the gradient. So it's telling you it's pointing in the positive direction towards the hill, essentially. Like if you go this way, you're going to go up the hill. If you go on the other side as you're coming down, df by dx is negative, right? So it's pointing in minus I. It's telling you, oh, the hill is in the other direction behind you. So we use grad phi, and so the same analogy applies also in 3 dimensions. The gradient of a scalar field always points in the direction of a local maximum, and it is local, not global. It is a local maximum. Okay, we were doing this 1D example last time, and let me hide this thing. Okay. So if you remember, we defined this function, this bimodal function. It has it's going up over here, and then it's coming down, and then it goes down, right? And the derivative here is positive, the derivative here is negative, so we know that over here is going to point in this direction. It's telling us keep going in the positive x direction to reach the hill. If you're on this side, it's going to tell you keep going. df by dx is negative, so go in the negative x direction, in the opposite direction, to reach the hill. Now you come down here, same. Here you're coming down, it's negative, it's going to tell you go this way. But once you hit this point, it's positive here. So it's telling you go this way for where? There's a local maximum here with respect to these points over here, right? So this is a local maximum, this is a local maximum. This entire range here is going to point to this hill, whereas over here is going to point to this maximum. Now over here it's just 0, there's nothing going on, but at least in this range it's going to point, you got to go in the positive x direction to climb that hill. Now a more interesting situation is when we do it in 2 dimensions. All right, so we're going to reuse whatever we did with our scalar fields last time, and I'll show you a couple of tricks on how we can compute the gradients very quickly using NumPy, numerically, okay? Without having, you can do, if you have the scalar field function analytically, compute the gradient analytically and implement it. That gives you the best accuracy. If you don't have it analytically, or you just are lazy, don't want to do it, just compute it numerically. Okay, so I'll show you how to do that here today. All right, so let's see. So actually, before I show you the other stuff. So I have this little thing over here showing you what the vectors look like. So this is the gradient. So in these locations, the gradient is pointing in this direction. It's telling me, go this way so that you reach the hill. But once you go here, it's negative. Once you're here, it's putting me in this direction. But then over here, it's pointing this way, and then it's 0 over there. Okay? I'll show you how to do a vector plot in a bit, but let's first learn how to compute the gradient numerically. All right. So we will keep this here and call this Fall 2025 gradient demo. And these Python excursions are taking up time from the class instead of spending time on the theory. But I think they're useful because we think about this theoretically, we never get to do it. It's good to see it numerically and practically. Okay? Gradient demo in class. Okay. In class. So we got all the boilerplate over here. And what I want to do is now define my two-dimensional Gaussian again. So let me see if we still have it from last time. Just go ahead and, what is it, scalar, fault, scalar field. So if you look at the scalar fields, if you go to your scalar field notebook that we did last time, okay, just please copy and paste this bimodal Gaussian, okay? So we're going to copy and paste this. And actually, I'm going to copy and paste all of these. I'm going to do this here and say 2D gradient. Okay, so just copy and paste these. If you remember, this was a double Gaussian, again, from that other plot that we did last time. Also, you can copy. I'm just going to keep it here. This one had two hills, right? And then we did this as a contour plot, right? So let's instead do this. So execute. Don't print these. You guys okay? You got these from the last time notebook from Tuesday? And I'm just going to put the contour plot again. Oh, of course, it's not defined. It should be Z is equal bimodal Gaussian, then XY, bimodal Gaussian, XY. Okay. So what should we expect for the vector field, for the gradient to tell us here? Both of these are peaks because they're all positive. This is a local peak, this is a local peak. We expect the gradient here, all of the gradient vectors, to be pointing towards the center. And then once we get closer to this one, for them to do the same, to be pointing toward that peak over there. Agreed? Okay, so let's do this. How do we compute gradients? There's a really neat, if you have the analytical formula, do it analytically. Okay, that gives you the best accuracy, and that will give you the best accuracy. Okay, but if you want to do it numerically, we can use what's called numpy dot gradient. Give me a second here. Second. Okay. NumPy dot gradient. So what we will do to compute the gradient, so I'm going to keep this plot here because I'm going to plot on top of it the vector field. So df by dx, so that's the first component of the gradient in the I direction. You simply do np dot, if I do np dot, whoops, gradient, okay, that's it. It's called np dot gradient. You give it f, in this case that's going to be z. Now, the way Python stores things, and this is the critical piece here for you to know, it stores data from the last dimension to the first dimension. So it stores it in z, y, and then x. It stores it in the array, so in this z array that contains all of these points. The data are stored first in the y direction and then in the x direction. So we take one x, fill all the y, and then the next x, fill all the y, and then and so on and so forth. So rows versus columns. The rows are y and the columns are going to be x. Okay? So to do df by dx, if you notice here, there's an argument here called axis. This is you're telling it differentiate with respect to what direction, x or y. Because it stores them as y and then x, or z, y, x, the first axis is going to be axis 0, the second axis is going to be axis 1, the third axis is going to be axis 2, and so on. This is a 2D case. The first axis is y, so that's 0. The second axis is x, which is 1. So here we had to do df by dx. We need to tell it, do it with respect to axis equal 1. Okay? So you say axis equal 1. Right? And then you do the same thing. We do the same thing for actually, hold on. There's a better way. Vector field. Actually, there's an even better way. So the problem when doing this, okay, never mind. Forget what I said. Forget what I said. Here's the better way to do it. If you do np.gradient, sorry, my apologies. Okay, if you do np.gradient, if you do np.gradient and give it y and give it y and x, not the mesh, but those y and x here, and give them in that order, this is going to do df by dy and df by dx for you automatically. So let me try this. Okay, there you go. It did it. All right. So keep that in mind. So if this is a three-dimensional function, you would give it z, y, and x in that order. Okay, in that order. Why do I need x and y? Because I need the spacing. What I did before would be technically incorrect, because numerically, what is it doing? It's doing a finite difference approximation. It's doing fi plus 1 minus fi minus 1 over 2 delta x, right? If it doesn't know delta x, it's going to assume it's 1. So it's not going to give you a scaled value of the gradient. Secondly, what if your spacing is non-uniform? What if you had what if you had logarithmic spacing in x, a lot of values as you go to the edge, or a lot of values at the beginning, a smaller spacing, and then the spacing becomes bigger and bigger. The only way to fix this is to give it x, y, and x. So this is the correct way to do it. Forget what I said earlier. It was incorrect. Okay? It was incorrect. Okay, so now we have the gradients. And we can plot them, bless you, we can plot them, but they're not going to be useful. The best way to visualize this gradient is to do it as a vector plot. Okay, so how do we do vector plots? We have to use something called the quiver. So here's what I'm going to do. For quiver, I can do ax dot quiver. Okay, quiver. What does quiver do? It plots a 2D field of arrows. It's essentially just a vector field. You give it, bless you, you give it the x and y locations where they find the origin of each vector. Okay, the origin of each vector. And then you give it the x magnitude and the y magnitude of the vector. Okay, so let's just do that real quick. So we already have a color bar up here. And so for here, I'm going to give it the mesh grid x and y, and then I'm going to give it the df by dx and df by dy. Let's see if it works. Plt.show, let me put that down here. Oh, yes, okay, awesome. It looks ugly, but it's a start. You see a bunch of arrows that you can't really visualize because there's a lot of arrows. They're like weirdly scaled, but they're pointing in the right direction. So let's clean this up a little bit. So Quiver is a very important tool that you will need to use, that you will use, I guarantee you, sometime in your research. Now, how do we make this better? If you're using like sophisticated software like three-dimensional visualization tools like TechPlot or Visit visualization, things like that, you would have buttons and settings where you could say skip every other vector or skip 3 vectors, right? You don't want a vector at every point because it looks very ugly, right? So we need a way to skip these vectors. It's not very easy to do it, but just if you do this, it will just work, okay? So do this, and don't ask me why they designed it this way. I think it's terrible, but it does the job. So if you do the following and you say skip slice, none, just do it this way, none, none. So what this is trying to do is trying to create a slice of these vectors, and what matters here is this number. I'm going to skip every other 3 vectors, or every other 2 vectors, or every other 5 vectors. If you have 2 million points, you probably want to skip every 20 vectors, right? Because it's going to be really, really dense. Okay, so if you do this, and then you come here and say x skip skip. So what this is doing is it's like taking a subset of this array. That's all it's doing. Skip skip, and then skip skip, and then skip skip. And you run it. It did something much better. Okay, it skipped it. It skipped every third vector. Now let's change the color. You can color them based on their magnitude or something if you want, or you can just color them with a fixed color. So I'm not going to worry about that. You figure out what kind of styling you want to do. So make them white now so they look a little nicer. And I'm going to give them a scale, and let's play with the scale. Let's say scale equal 10 or scale equal 50. It makes them a little smaller. Okay, this is much better now. I think let's do 40. Okay, did you get this? You guys get this? Yeah? Okay. Yeah. It's not a lot of code, but it's sort of intense. But we learned two great things: how to do the gradient really quickly, numerically. Right? So now you have the gradient. It gave us the 2 components, df, dphi, dx, dphi, dy. And then we put them in a vector plot. And as expected, look, the gradient is pointing to the local maximum. Always pointing to the local maximum. As expected. It's not pointing to the global maximum, just to the local maximum. Okay, you need one more minute here. Can I come back to the slides? Yeah? All right. Okay, good. We Pythonified this. Another thing we can define with gradients, it's what's called a directional derivative. So the gradient itself defines a direction, and that direction is towards the local maximum. Okay? That's it, period. But what if you are at a point in space, and okay, so I know the gradient is pointing in the maximum, but I want to compute the slope in this direction for it. The gradient is giving you the slope in one direction towards the maximum. But what if you want to compute the slope in some arbitrary direction? So that we call that a directional derivative, and we designate this as dv of phi. So that's a derivative in the direction of the vector v, arbitrary vector v of phi, and that's defined by the ratio of vector v over its magnitude, to normalize it, dot the gradient of phi. So you still need to compute the gradient. So you have the gradient slope, but then you want the slope in some other direction. You just adjust that direction by taking the dot product of this normalized direction, v over magnitude of v, dotted with the gradient. Okay, it measures the slope at a point in a specific direction. So it's like saying, okay, I have this scalar field. It's doing something. Okay, it might be pushing ink. It might be pushing information some way. But what if we choose to go in that direction? What is the slope if we go in that direction? What is the resistance to climbing that direction? Okay, this becomes helpful when you're computing, for example, energies and work. Okay. The next type of, so that was the first operation with the Nabla operator. It's called the gradient. The next operation is called the divergence. The divergence is very important. It's very, very important. In fact, with divergence alone, we can derive nearly every differential equation from the great conservation laws. I'll show you all of that later. It's a very important tool, the divergence. The divergence operates on a vector field. Gradient operates on a scalar field. It gives you a vector. The divergence operates in a vector field, and it's simply what? The dot product of the Nabla vector with the vector of interest. So that's where it comes in handy to think of Nabla as a vector, because you're simply doing a dot product between two vectors, except that this vector is an operator. So when you say d by dx times u, it's not times u, it's d by dx of u, right? So du by dx. And then you just operate this as a standard dot product, a1b1 plus a2b2 plus a3b3, and you get a scalar, just like a standard dot product gives you a scalar. A standard divergence of a vector field gives you a scalar. So result of a gradient is a vector, result of divergence is a scalar. We also write this as div u. So people come and say del dot u or Nabla dot u, and you can use those words. Just say div u. Grad phi div u. No use of Nabla or del dot u, just div u. It's actually more meaningful because del dot u is the mathematical wording of the divergence, but divergence carries meaning. Del dot, it hides that meaning. So if you were me, if I were you, I always use grad, div, and curl. Okay? So div u. Now, you've seen the divergence, I hope. Okay? What does it mean? So gradient, we put that in the books, right? It tells us about where local maxes are. What about divergence? What did you learn? What did you know? You guess, or if you remember something.
It diverged from the true.
But what true value? So it's diverging from something, right? But what is that? I mean, you're not wrong, but there's something more specific there. So we call it divergence, right? So these are vectors. They're diverging from what? So what if you take a point, you say, if divergence is positive, what does it mean for the vectors at that point? If the divergence is negative, what does it mean? If the divergence is 0, what does it mean? Are they diverging away from that point? Are they diverging into the point? Convergence. Or they're not diverging at all? Okay, this is exactly it. Right. So what I'm going to do next, I'm going to show you numerically, on a small volume, numerically, what the divergence means. I'm going to consider a random vector field given by these black arrows. And this vector field, I'm going to call it velocity. It doesn't have to be velocity, but most of the time, these ideas come from fluid flow. So they came out from velocity vector fields and displacement, speed of displacement in continuum mechanics. So velocity is in meters per second, or length. The dimensions of the velocity are length per time. The units we've chosen are meters per second. So this is given in black here. And I'm going to choose an arbitrary rectangle. It doesn't matter its size. It doesn't matter its shape really. But I chose a rectangle because it's simpler to do what I'm going to do. Okay, now into this volume, this flow with this velocity is coming in and leaving. Okay? Now, because we are in a Cartesian coordinate system in 2D, vectors like this are going to be like a vector that is not going into the volume is going to be parallel to this, is not going to be useful. So I need to look at the vectors that are going in and that are leaving the control, this little red box, right? And because we are in 2D, we can decompose. So suppose there's a vector here coming this way, then I can decompose it into a U component and a V component. And suppose the decomposition looks like this. It doesn't have to be like this. It could be they're all going in here and leaving from this side. It doesn't matter. But what matters here is that at this point, I have a U component coming in. And if this rectangle is so small, then at this point, it's U plus some difference. This could be negative or positive. If it's negative, then this one is smaller than that one. If it's positive, then it's a little bit bigger. Okay? So it doesn't matter. But keep in mind that we've just moved a little bit. This is U, and this is U plus delta U, some change in velocity at this point. Same thing at the bottom. I care about the V component only because it's the V component or the Y component that's bringing things into the control volume. This component on these surfaces, on these faces, doesn't bring in anything to the volume, right? They're just kind of passing by. Okay? Okay, next I want to compute the net outflow through the volume. In other words, I want to compute in total, is there mass coming out? How much mass or how much volume, assuming the density is constant, so it's 1, say, and no density is involved. How much volume is coming through this little rectangle? It's very simple. If you remember your fluid mechanics, the volumetric flow rate through an area, through a face, it's the speed times the area. U times A, so meters per second times meters squared gives you meters cubed per second. That's volumetric flow rate, right? There's no kilogram per second because there's no density, and it's not a mass flow rate. Density is constant. So it's a volumetric flow rate. It's technically the flux. Okay? So I have, over here, I have U times delta Y, and assuming unit depth, delta Z equal 1. And over here, I have U plus delta U, also times delta Y. Now, if you remember our mass conservation principle, which we did early in the class, in the x direction, I have U plus delta U times delta Y minus U times delta Y. So what's coming out minus what's going in, supposedly. Okay? Now, this delta U could be negative, and it will change the signs, but it doesn't matter. And same thing in the y direction. I have V plus delta V times delta X times delta Z equal 1. Right? So here, delta Y, this is delta Y times 1 meter. So this is in meters squared here. This is an area, except in 2D, it looks like it's 1 meter in depth into the board. And same thing in the y direction, U plus delta V plus delta V times delta X minus V. Now, I prefer to write these on the board, but we have to do it on slides this year. The dimensions of Q are length cubed per time. It's meters cubed per second with the units we chose, because this is meter per second times meter squared, right? So delta Y, this is delta Y times delta Z technically, and delta Z is 1. Okay? So this is my Q. If I run the numbers, I have Q equal delta U times delta Y plus delta V times delta X. Okay, good. So that's my net flow through the volume. Now, if I divide, I notice something here. Well, I want to turn these. I always like to think in terms of derivatives. These, mathematicians and physics people, they want rates of change. Well, to get a rate of change, I need like delta U over delta Y or delta U over delta X, right? I need this infinitesimal change or in the dependent variable over a change in the independent variable. What we would do here, we divide by the volume. If we were to divide by delta X, delta Y times delta Z, so this is volume of this rectangle, then I start getting something that is going to look like a derivative, because as I shrink this volume, this is going to become partial derivatives. And this is exactly what happens. So in the limit, as my volume approaches 0, both delta x and delta y are approaching 0 independently. This turns into derivatives. du by dx plus dv by dy, which is nothing more but the divergence of that velocity field. Okay? This is the first shell balance analysis we do here. But the point here is that so what is this? Q over V is the net outflow of volume per unit volume. That's what the divergence is. It's a handful, it's a mouthful. So let's see what this means. If div u is positive at a point, it means per unit volume at that point, there's a net outflow of volume coming out of that vector field. It's diverging. If div u is negative, there's a net, so the net outflow of volume is negative. It means there's a net inflow into the point. And if it's 0, there's no net inflow or outflow. Whatever is coming in is leaving. What is the condition for incompressibility? So whatever is coming in should leave. Mass cannot be compressed or changed in any way, right? And we will show that this will be the condition for incompressible flow. Okay? But this is the divergence. Now, when you think about the dimensions of the divergence, they are dimensions of the vector per unit length. Specifically, if u is a velocity field, meters per second, over meter, it will be 1 over second. Okay? It's like a frequency, right? It's like a frequency. Okay. A vector field with div u equals 0 is said to be incompressible and also divergence free. So there's no divergence in it. When I tell you divergence free, it means div u equals 0. Now we will study that this would be a necessary and sufficient condition for a fluid flow to be incompressible. The divergence operator is also linear. Div of alpha u is alpha div u, and div u1 plus u2 is div u1 plus div u2. There's a little typo over here. Fix that. Div u1 plus div u2. All right, Laplacian. Okay, so what do we have in the books now? Gradient, we know what it means. It points in the direction of local maxima. Divergence, it tells us if the flow is converging to a point, leaving a point, or everything is coming in and leaving, going through. Okay? What it means in the context of fluid mechanics and transport for chemical engineering is that if div u is 0, it means the flow is incompressible. Whatever is, you cannot squeeze things into a point. The next thing we will look at is the Laplacian. Who remembers the Laplacian? Laplacian? You remember the Laplacian? We did it in 1D. That's the heat equation. Second derivative of temperature, right? That's the Laplacian in 1D. Okay. This is really cool now when we start combining divergences and gradients, etc. What happens if you take the divergence of a gradient? Gradient of a scalar is a vector, right? So that's a correct operation. Divergence is applied to a vector. So what if you do the divergence of a gradient? What you get is the following. If you do it, if you just take the dot product of the nabla operator with the gradient of phi, and you do the dot product, it's d by dx of d phi by dx and plus d by dy of d phi by dy, etc. You get a bunch of second derivatives. And this is a scalar. Because the divergence always gives you a scalar. So this is div of grad phi, but the div is always going to give you a scalar. Okay, so it's a bunch of second derivatives. What does the Laplacian tell us? What does it do? What does the second derivative test tell you in one dimension? Yes? Concavity, right? If the curve is concave down, does it have a hill, or concave up, does it have a trough, right? That's not the case in 3D. Sorry. It's close. It's close. For most cases, the Laplacian will tell you about the concavity of a function, of a scalar field, because in the end, we're applying Laplacian on phi. Yeah, and I didn't, you should have used the symbol here. This is also equal to what we call del squared phi. Okay, my bad. It's equal nabla squared phi. Okay. So the Laplacian applies directly on a scalar field, right? It's del squared phi. It can tell you about the concavity of a function except for scalar fields that have saddle points. What's a saddle point? It's like a horse saddle. In one direction you have a maximum, in one direction you have a minimum. The Laplacian is going to be exactly 0 there. It doesn't tell you anything. Okay? So in general, use it wisely. To truly tell about the min and max information or the concavity of a function, you need to use what's called the Hessian. But this will do. You know, it's a back of the envelope calculation to tell you if you are close to concave up or concave down. In other words, this is trying to tell you if you are at a local max or a local min. The gradient always told us where the local max is. Okay? But the Laplacian can tell you if you are at a local max or a local min. And here's how this works. If the Laplacian at a point is positive, you might be possibly at a local minimum, but definitely you're not at a max. Okay, so what you can tell is you're definitely not at a maximum, but I might be at a minimum if del squared phi is positive. If del squared phi is negative, possibly a local max, but definitely not a min. Okay, now this becomes weird and kind of untractable. So let me show you a finite way of making sense of why this would be a local minimum, local maximum, etc. More specifically, the Laplacian at a point, at some point A, is related to the average value of the scalars around that point. And it specifically measures the deviation from the average. So let me explain what this means. So I'm going to do this in one dimension because it's simple. And I'm going to take this curve. It doesn't matter if this point is higher than that point, it's just a description. This is my point A, and this is distance epsilon or h away from A, so A plus h, and this is A minus h. H is going to go to 0 eventually, but it's not going to matter. We're going to do this numerically just to give you a sense of what the Laplacian means. Now, in 1D, the Laplacian is nothing more than the second derivative. So d2f by dx squared is approximated as f of a minus h minus 2f of a plus f of a plus h over h squared as h shrinks to 0. Okay, very good. We agree, right? Okay. So now what happens? I'm just going to ask the question, what if what does it mean when this is equal to 0, when d2f by dx squared equal to 0? If that's equal to 0, then this implies that, you do the math, f of a is the average of the neighboring points. F of a minus h plus of f of a plus h over 2, the literal average of the neighboring points. Remember, h is approaching 0, but it only appears in these, not in the denominator anymore. This is really cool. When the Laplacian is 0, it means the point is literally the average of two neighboring points. Okay, as close as you want to be, it's always going to be the average of two neighboring points. Okay, now the interesting question is, what happens when it's positive or negative? When d2f by dx squared, or the Laplacian, is negative, then the value at the point in question is greater than the average of the neighboring values. What does this mean? That you are possibly at a local maximum, okay, because you are greater than the average of the neighboring points. And the opposite is true. If the Laplacian is positive, then the value at the point is smaller than the average of neighboring points. So you are most likely at a local minimum, at a local dip. Okay? So you take this to heart as well. If the Laplacian equals 0, then the value at a point is equal to the average of neighboring values. If Laplacian is positive, then the value is less than the average, or you can interpret it as the min-max interpretation. But anyway, this is what the Laplacian tells us. If del squared phi equals 0 everywhere, we call phi a harmonic field, a harmonic function. All potential flows obey this condition. If you've heard of potential flows, if not, doesn't matter. Okay. Okay. So let's see. We have some time. Let's do this in Python. Okay. Let's do this in Python. All right. So we can continue. Let me see what I have here. Visualize scalar field. Visualize Laplacian. Okay. Let me see how I did this. Okay, so now for the Laplacian, I need to do, let's try this. All right, I need to do the gradient of this, right? Another one, another operation. So what I'm going to do next is d2f dy and d2f dx is equal mp dot gradient of, well, okay, hold on. This is not going to work this way because this is df by dy. And if I do df by, let's see, I have to do them separately. Okay, I have to do this separately. Okay, I have to do this separately. So let's try this. Let's do d2f by dy squared, or dx squared, is equal to mp dot gradient of df by dx, okay, and axis is equal to 1. Okay, so let's take this. Axis is equal to 1, and I'm going to provide it with the value x. Okay, so let's see if this is going to work. Yes, it worked. And then d2f by dy squared is mp dot gradient of, let me see, is there a Laplacian? Nope. P dot gradient of df by dy, and I'm going to give it the y coordinates, and axis equals 0. Remember? Because df dy, df dx, it's a two-dimensional array, but it's stored in the order y and then x. Okay, so you got to tell it which derivative you're taking. And then finally, Laplacian d2f, let's call it, or is equal to d2f by dx squared plus d2f by dy squared. Okay, so that's another field. And now I can finally plot this. So let's plot it. Let's copy the and this is going to be a scalar, so we will plot it as a contour. Okay, Laplacian contour. Might look a little weird because you're doing two derivatives, and the way you might get in trouble at the boundaries, because the way is going to approximate those derivatives at the boundaries. So I would not worry about the boundary points. The only way to fix this is to go and manually fix the boundary points. How you do that, like boundary conditions. Okay. But if you have an analytical solution, just use the analytical formula. Otherwise, this is just as good. Okay. So let's see, d2f, and we have 10 levels, and we're gonna plot. All right. So it did this. Now the levels are messed up, are wrong. So I'm gonna do 10 levels here. Okay. So now it's giving me a Laplacian. Okay, and it is negative here, right? And it is negative here, indicating a likely local max. Remember, Laplacian is the opposite. If it's negative, it means it's a max. If it's positive, it might be a min. Okay? And everywhere else, it's just 0. Okay, there's no max or min everywhere else. Okay? This is at least consistent. In this case, it works great. Once you have saddle points, you cannot use the Laplacian to determine concavity. It will be 0 at the saddle point. So be careful. Don't go say Professor Saad is telling us the Laplacian tells us about min and max. My reputation is on the line. Okay. You good with this? See what we did here? I had to separate them separately because I had to do the second derivative of this, second derivative of that, and watch out for the axes. Okay? Can I go back to the slides? Okay. So we did gradient, divergence of gradient. So the divergence was, when we talked about vectors, we talked about two types of products, the dot product and the cross product. The divergence represents the dot product of nabla and a vector. We haven't done the cross product, so can we do the cross product of nabla and a vector? Yes, totally. And that is called the curl of a vector field. So if you take the curl of a vector field in 3 dimensions, it is the determinant of this matrix, just like you would do normally a standard determinant and you multiply and subtract, etc. You just do it here with operators. So d by dx times v is really dv by dx. So you're applying an operator to the thing, and then you get 3 components. You get a vector as the result of the curl. Okay? And the curl, obviously the next question I'm gonna ask you is, what does the curl mean? Okay, the curl is related to the vorticity. Oh, wow. With the vorticity, the curl and the vorticity, they measure how much if you were to put a drop of ink at a point in a fluid, at that point, how much it's going to turn. What is the rate of that point turning around in the fluid? It's a measure of that. Now, to prove it to you, I'm not going to prove it actually, because it's going to take about 15-20 minutes. So I will leave the proof here. The proof is self-descriptive. No, it's just math. Maybe I'll do it some other time or do a short video. Anyway, yeah, it's just easy, just piece of cake stuff. You're all geniuses and you can determine. Anyway, so it does measure. The point is that it measures, the curl measures rotation. Okay? If there's no curl, it means there's no rotation, and the flow is irrotational. Okay? So potential flows, they are curl-free. They have 0 curl. Remember, the curl is a vector. So if your result is 0, you have to put 0 with a vector on top of it, not a scalar number. 0 with a vector on top of it means 0, 0, 0. Right? So be careful. You'll lose points for that. Okay, next, I want to get to the integral theorems. And to get to the integral theorems, I need to define unit normals. A unit normal vector to any surface S is any vector that has magnitude 1 and that is normal locally at the surface. It could be pointing in this direction or that direction. If this surface is an open surface, there's no preference to where the unit normal is pointing towards. It could be pointing this way or pointing that way. As long as its magnitude is 1 and it's normal to the surface locally at that point, then this is called a unit normal vector. Typically, you will see this in integrals. You see n ds, where ds is a surface element. Let me fix this. Okay. So you'll typically see this, as we will see next. This would be a small surface element on that surface. Now, when you have a volume that's enclosed by a surface, so the surface has inside and outside, then you can define a very specific unit normal vector, and that's called the outward unit normal vector. The outward unit normal vector on a volume is the unit normal on the surface of that volume that's always pointing away from the interior. So if this is a cylinder, let's say, the unit normal here is this guy, the unit normal along the circumference, it's always pointing away from the interior. Always away from the interior. Once you have a volume, you define that surface enclosing the volume. At every point, the unit normal, the outward unit normal vector is always pointing away from the interior towards the unbounded domain. It's very important, because that is the critical definition of the great integral theorems. Everything is great in this course. The great conservation laws, the tuning forks of psi. The integral theorems, anyway, they're not, there are the tuning forks also of like conservation, but they are, I like to call them the great integral theorems, okay? I will talk about two today. We might need to talk about a couple more, but these are the two important ones. The first one is called the gradient theorem, and whenever I write an integral over a volume, I could put triple integrals or a single integral over V. You should automatically assume that this is a volume integral. If the volume is in 2 dimensions, I'm assuming unit depth, so it would, that volume integral is a double integral really. The point is I'm integrating over a volume, and once you have a volume, you have a surface enclosing that volume, well-defined surface enclosing that volume, okay? And then you can define the outward unit normal on that. The gradients theorem tells us that for any scalar field that's continuous and differentiable, we're assuming all of those, the volume integral of the gradient inside the entire volume. So you have a volume, and you have phi inside it, and you can calculate the gradient of phi. Remember, grad phi is a vector, but you can compute grad phi in it. Then the volume integral of that grad phi, you're summing up all of those grad phis at every point in that volume. That's equal to the surface integral of phi at the surface, so only at the surface, in the direction of the outward unit normal. This is an incredible theorem. It's like almost unbelievable, but it is super useful because we will use that theorem to figure out what we do with the pressure and fluid flow. So I'll give you an example. Suppose that this is a scalar field. So this was the Taylor vortex, which we talked about last time. And I'm going to define an arbitrary volume. Now in 2D, it's going to look like a disk or something, just like a closed shape. This is the surface enclosing my volume. Could be an arbitrary surface, arbitrary shape. It doesn't matter. Okay? Inside the volume, I have a gradient of phi, right? There's phi is positive here and then going down. So there's a gradient in all sorts of directions. The claim is the sum of all of those gradients inside this volume is equal to the sum of the value of phi, so the scalar value at this point. There's this red value. At this point, there's this blue value, integrated across the entire surface and pointing in the direction of n. So when you add up the n's, well, each n has two components, x and y in this case. You add up all the x components, and you add up all the y components, and you can compare that here. This is a vector equation. Why? Because grad phi is a vector. So you're integrating in I, j, and k. And same thing here, n, this is a vector equation. Phi is a scalar times a vector. It's a vector. Okay? So do an example. Let's do an example. Again, I would rather write this down, but the slides will do. You have to review this at home to make sure it makes sense. So I'm going to take this scalar field given by x squared plus y squared. It's like a paraboloid. And it looks like this. It's 0 here, and then kind of starts going up over here at x equal 4 and y equal 3, etc. So there's values given by this color. And the gradient of phi is shown by these arrows. Okay? And they're scaled by size. So look inside this volume that I'm defining here, simple rectangle, going from 1 to 3 and in the x direction and 1 to 2 in the y direction. There's vectors inside it, right, in all sorts of orientations. And I want to show now, to demonstrate this theorem, that the volume integral of grad phi inside this volume is equal to the surface integral. The value is only at the surface. Okay, I was doing this morning, actually. I made a mistake. I was like, oh, crap, is everything wrong? And then I had a little typo, so, which I will use to trick you in the homework and the exam. Okay? Yep, exactly. Okay, so let's do the volume integral. Sorry, no animations here, but we have to go from top to bottom. So if phi is x squared plus y squared, that's my identity, the gradient theorem, that the volume integral of grad phi is equal to the surface integral of phi and ds. Grad phi is simply 2xi plus 2yj, right? d phi by dx, I plus d phi by dyj. Okay? So volume integral of grad phi dv is the volume integral of 2xi plus 2yj dv. Okay? Which means now this volume, I'm integrating over the volume. I'm integrating in x and y. Okay, so that's in the I direction, so that's two equations, two terms. First, the I term is integral of 2x dx dy going from 1 to 3 and then 1 to 2. So going from 1 to 3 in x and from 1 to 2 in y. And I put x in the interior first because we're integrating in x, like 2x, and this is x squared from 1 to 3, and so on. So this is going to give you 8. And this one is the integral also of 2y in the j direction, dy dx or dx dy, doesn't matter, but I did it dy dx because we're starting with y, going from 1 to 2 and then 1 to 3, so totally legit. This gives you 6. So the result of this volume integral is 8i plus 6j. It's just a number, it's a vector, it's a net vector, 8i plus 6j. Okay, good, this was easy. Now we want to demonstrate that this is equal to the surface integral of phi and ds. Okay, this will look more complicated, but actually clarifies a lot of things. Now, thankfully, this is a rectangle, so the surface is discrete. So the surface integral of phi and ds is equal to the surface integral on each one of those surfaces. The sum is equal to the sum, right? Because these are discrete surfaces, well defined. So I will define S1 as this surface, and this is the outward unit normal, and 1 is I. Surface 2 is the top surface. The unit normal is J. Surface 3 is this surface. The unit normal is what? Minus I, is the outward unit normal. And this is S4. The outward unit normal is minus J. Okay? This total surface integral is the sum of the surface integrals for each one of those faces. So for S1, I'm saying my theory is telling me this is the integral over S1 of phi n hat ds. So what is phi at S1? X equals 3 here. Y is changing from 1 to 2, correct? So I have this phi at x equals 3 because I'm evaluating phi at that surface. And at that surface, x equals 3. Okay? So phi at x equals 3, y, all of y. What is the unit normal is I. And it's a constant, so it comes out of the integral. I will give you a problem where the unit normal changes along the surface. So you have to keep it inside the integral. Be careful. Okay? So in this case, I is constant across the entire surface, so it's going to come out. Same thing for S2. For S2, y is equal to 2, but x is changing. Okay? And this is pointing in the direction j. So n hat is j here. N2 is j. And it's a constant. It doesn't depend on x or y. So I'm going to pull it out. And then go to S3. Right? Phi at S3, x is constant. It's equal to 1. So I'm going to put x equal 1. And y is changing from 1 to 2. But this is pointing in the minus I direction. So n hat is minus I. It comes out because it's a constant. So you have minus I and so on. So now you can see how what looked like a mystery integral, this is nothing more than two components. An integral that has two components in it. Some in the I, some of them in the j direction. You start substituting, so I'll do one of them. So for this S1, we said x equals 3 and y is changing. So this means if phi is x squared plus y squared, this means phi on this surface is 9 plus y squared. And I'm integrating this over y from 1 to 2 in the I direction. And you do the rest of these. You combine them together, you get 8i plus 6j. Same as before. The previous answer was 8i plus 6j. It is true. For an arbitrary shape. Okay? These are very useful theorems. Okay, it's a very useful theorem. The more important theorem is called the divergence theorem, also called Gauss's theorem or Gauss-Ostrogradsky's theorem or Ostrogradsky's theorem, but Gauss takes all the glory. So let's call it Ostrogradsky's theorem, just to give him something. Okay. This is saying, so this is the scalar equivalent of the gradient theorem. It says that the volume integral of the divergence of a vector field, so now it's just a scalar, but you're working with a vector field. You take its divergence, it's a scalar field. The volume integral of this scalar field on an arbitrary volume is equal to the flux of that vector field through the edges of that volume. U dot n, so n is still the outward unit normal. U dot n is finding, remember, the dot product shows you how much these vectors are pointing in the same direction. So when you do U dot n, you're taking only in the direction of the outward unit normal, and U, like that common direction. So what this is saying is, whatever divergence you've accumulated in the volume is equal to whatever is coming in and out of the volume, right? Which is kind of the statement we were trying to make earlier when we did the infinitesimal volume. But this is expressed in an arbitrary form. Any volume that has a well-defined surface, okay, this is true. Now, you will find that this theorem single-handedly, this integral, single-handedly is responsible for every transport equation that we look at. Advection, diffusion, reaction equation, Navier-Stokes equations, all of these transport equations, they come from the application of this integral theorem. So we will see this starting after the fall break. I'll show you how we build the conservation laws just with integrals, and then we will have divergences that we will convert to surface integrals or surface integrals to volume integrals, and then make everything equal and clean it up. But single-handedly, this theorem is responsible for all of these differential equations. Okay, it's very useful. Again, we can do the same exercise we did previously on a small rectangle, scalar field, etc. You can verify that. But this is called the divergence theorem or Ostrogradsky's theorem. Okay. Next, I will briefly go over other coordinate systems. So obviously, there's, in 2D, we have polar coordinates and 3D cylindrical polar coordinates that you can define on cylinders. So I'm not particularly necessarily going to spend time on this because we're not going to be deriving, like if we were teaching fluid mechanics and we'd be doing solutions of flow over a cylinder, for example, or like flow between two concentric cylinders, etc., then you would need cylindrical coordinates. But you should just know them. You will have a couple of homework assignments on those. And I'm assuming, so a point in space can be defined in the Cartesian plane as in ijk, but in the cylindrical coordinate system, ER, E theta, and EZ. Now be careful, ER and E theta do not point in the same direction. So this is very careful. They change with position. So let's say E theta over here is pointing in this direction, but over here is pointing in that direction. Over here is pointing in this direction. So ER and E theta are an example. If you're doing an integral, a surface integral with a unit normal or something, it's going to change as you move along the surface. So you cannot take it out of the integral. Be careful with that. Unlike ijk, I over here is, let's say this is the x-axis. I over here points this way, and over here it points this way. But if I was on a big circle here, this is E theta here, and then over here this is E theta, and over here this is E theta. Okay? The cleanest way to do it in those cases is to convert them to Cartesian form. Cosine theta I plus sine theta j. Okay? So, and this is what I'm talking about. ER is cosine theta I plus sine theta j. So it changes direction as you move along position in space. Same thing for E theta is sine theta I plus cosine theta j, and EZ is just k pointing in the k direction. And the rate of change of ER with respect to theta, so again, if you are traversing some vector operation along the circumference of a circle, so you're traversing in theta, the rate of change of ER is going to be equal to E theta. And the opposite is true. The rate of change of E theta with respect to theta is minus ER. Okay, so you'll keep those identities. We'll use them later when we are deriving equations. Similarly, the nabla operator changes form when you go to cylindrical coordinates. So here we had d by dx, d by dy, d by dz, but in cylindrical coordinates, it's d by dr, 1 over r d by d theta, and d by dz. Why do you need the 1 over r here? Just looking from a dimensions perspective. The reasoning behind having 1 over r is because theta is dimensionless. Radians is no dimensions in angle. Don't make the mistake of saying, oh, the angle is in degrees. No, that's not a natural, that's just a simplifying unit, okay, for normal people, but we are not normal people, right? So theta is dimensionless. 1 over r gives it the dimension of 1 over length, because the gradient is 1 over length. 1 over length, 1 over length, this would make it 1 over length, same as here, okay? And then you would apply it. Now the divergence changes a little bit. Again, so you have to use this formula. It's not simply just the dot product of nabla and u. You have this kind of weird term here, 1 over r d by dr of r ur. So it changes a little bit. But the gradient stays the same, gradient of a scalar. The divergence is no longer simply the dot product of nabla with u. Okay, so you cannot really treat it as a vector nabla dotted with vector u. But these are standard formulas that will be given and provided as needed. Okay? And with that, we're done with kind of this vector overview. We will exercise these vector identities and thinking about vectors once we start deriving these differential equations, because I will invoke, remember the divergence theorem, remember the gradient theorem, and you realize why they're useful in that case. We're done for the day. Have a good weekend. Have a good fall break. Good luck with everything. I'll see you in a week. Thank you.